Welcome to our comprehensive guide on computer-aided design, or CAD. In this video, we'll explore the fundamental concepts, terminology, and practical applications of CAD theory and graphics. Whether you're preparing for an exam or seeking to enhance your understanding of CAD, this journey will cover everything from basic commands to advanced modeling techniques. Let's start by understanding what CAD is, and why it's so essential in modern engineering, architecture, and design. CAD replaces manual drafting with digital tools, enabling precision, efficiency, and easy modification. As we progress, you'll see how CAD impacts industries and everyday life. Computer-aided design, or CAD, is the use of computer software and hardware to assist in creating, modifying, analyzing, and optimizing designs. CAD enables designers to produce technical drawings and 3D models with unmatched precision and speed. Instead of relying on manual drafting, CAD offers digital tools that streamline the design process for engineering, architecture, and product development. This shift has revolutionized how professionals approach design, making it easier to visualize, simulate, and document their ideas. CAD is now a cornerstone in industries ranging from automotive to medical devices. CAD involves three major activities: geometric modeling, engineering analysis, and drafting documentation. Geometric modeling is the process of creating mathematical representations of real-world objects, such as wireframe, surface, or solid models. Engineering analysis uses these models to simulate performance characteristics, like stress or heat flow, allowing designers to optimize before prototyping. Drafting and documentation generate accurate technical drawings, blueprints, and assembly instructions from the models, ensuring clear communication with manufacturers and clients. Each activity is vital for transforming ideas into tangible products. CAD's relevance in today's society is immense. In architecture, CAD helps create building designs, 3D renderings, and precise construction drawings, reducing errors and costs. Manufacturing relies on CAD CAM for designing machine parts and programming CNC machines, enabling automated high-precision production. The medical field uses CAD for prosthetics, implants, and medical imaging analysis, while automotive industries simulate crash tests and aerodynamics virtually. CAD is also crucial in electronics, education, environmental design, entertainment, and gaming, offering time and cost savings through digital prototyping and simulation. Liquid crystal displays, or LCDs, operate by modulating light using liquid crystals. Unlike CRTs, LCDs require a backlight to produce visible images. The liquid crystal layer is sandwiched between polarizing filters, and electrical voltage controls the passage of light. TFT LCDs use transistors for each pixel, enabling high resolution and fast switching. LCDs consume less power, are flat and thin, and produce sharp images at their native resolution. These features make LCDs ideal for laptops, tablets, and monitors, offering clear visuals and energy efficiency. CAD systems utilize various input devices to facilitate design. The keyboard is essential for entering commands, coordinates, and text. The mouse or digitizer puck allows users to point, click, and select objects, with digitizer tablets enabling direct tracing of drawings. Scanners convert paper drawings or photos into digital images for CAD reference. These devices streamline the workflow, making it easier to interact with complex models and drawings. Efficient input devices are crucial for productivity and accuracy in CAD environments. Output devices in CAD include plotters, printers, and monitors. Plotters produce large-format technical drawings with high precision, often used for engineering and architectural plans. Printers provide physical copies of CAD drawings, with laser printers offering high-quality output and inkjet printers handling color. Monitors or displays are the primary visual output, allowing designers to view and interact with models in real time. High-resolution monitors are preferred for CAD work, ensuring clarity and detail in complex designs. CAD, a hatch is a pattern of lines, dots, or shapes used to fill a closed area in a drawing. Hatching is commonly used in cross-sectional views to represent different materials, such as steel, concrete, or wood. AutoCAD's hatch command allows users to select predefined patterns or create custom ones, enhancing clarity and material identification in technical drawings. Hatches are essential for distinguishing between various components and improving the visual communication of design intent. Layers in CAD function like transparent sheets, organizing different types of drawing information. Designers group related elements such as dimensions, text, or electrical wiring onto separate layers. This allows layers to be turned on or off, locked, or assigned unique colors and line types. Layers enhance organization, clarity, and control, especially in complex drawings. By managing layers effectively, users can streamline editing and maintain consistency throughout their project. Block in AutoCAD is a named collection of objects combined into a single entity. Blocks represent frequently used symbols or components, such as doors, windows, or bolts. They can be inserted multiple times in a drawing, reducing repetition and file size. Blocks streamline design workflows, ensure consistency, and make editing easier. Modifying a block definition updates all instances, and blocks can contain attribute data for bills of materials, making them invaluable in CAD projects. Blocks offer several advantages in CAD. They enable reusability, allowing designers to insert the same element multiple times across drawings. Consistency is maintained as repeated elements look identical. File size is reduced since repeated geometry is stored once. Editing is simplified, modifying a block updates all instances. Blocks can be stored in libraries and shared across projects, and they can contain attribute data for part numbers or cost. These features make blocks essential for efficient and organized CAD design. Close a file in AutoCAD without exiting the program. Use the close command. You can type close in the command line or select close from the file menu. AutoCAD will prompt you to save any unsaved changes. Choose yes to save, no to discard, or cancel to return to the drawing. The current drawing closes but AutoCAD remains open, allowing you to open or create another drawing. This workflow ensures you can manage multiple projects efficiently. Add a new layer in AutoCAD. Open the Layer Properties Manager by typing Layer or clicking the Layer Properties button. Click the New Layer button and a new layer named Layer 1 appears. Enter a descriptive name, set the color, line type, and line weight as needed. Click OK or close the dialog. The new layer is now available and you can set it as current to draw on it. Layers help organize and control the visibility of drawing elements. Add supports various dimensioning styles to measure and annotate drawings. Linear dimensioning measures horizontal or vertical distances. Aligned dimensioning measures the true length of inclined lines. Angular dimensioning measures angles between lines. Radial dimensioning measures the radius of arcs and circles, while diameter dimensioning measures the diameter of circles and arcs. These styles ensure accurate communication of measurements and design intent in technical drawing. Dimensioning CAD consists of several key elements. Extension lines are thin lines extending from the object to indicate the extent of the dimension. The dimension line, usually with arrowheads, shows the direction and measurement. Arrowheads mark the limits of the dimension. Dimension text displays the numerical value placed at the center or above the line. Leader lines connect the dimension text to the feature being measured, especially in radial or diameter dimension. These elements ensure clarity and precision in technical drawings. AutoCAD uses system variables like strtup and filedia to control user experience. Startup determines whether the startup dialog box appears when beginning a new drawing session. filedia controls whether file dialog boxes are displayed during file operations. Setting filedia to 1 enables standard dialogs for commands like open and save, while 0 suppresses dialogs, requiring file names to be entered directly. These variables help customize workflow and streamline operations. Text can be added in AutoCAD using single-line or multi-line methods. The text or dtxt command creates single-line text objects. Each line is a separate entity. The mtxt command allows multi-line text, where you define a boundary box and use a text editor for formatting. The style command sets font type, height, and other properties globally. Text annotations are vital for labeling instructions and notes in technical drawings, ensuring clear communication. Grid in AutoCAD is a pattern of dots or lines displayed on the drawing area at specified spacing. It acts as a visual reference, helping users judge distances and align objects. The grid is not printed and serves only as a drawing aid. Grid display can be toggled with the F7 key or the grid command. Adjusting grid spacing helps tailor the workspace to project requirements, improving accuracy and efficiency. Crosshairs in AutoCAD refer to the cursor, displayed as two intersecting lines forming a plus shape. They indicate the current position of the cursor in the drawing space. The size of the crosshairs can be adjusted through display settings, allowing users to customize their workspace for comfort and precision. Crosshairs are essential for accurate placement and selection of drawing elements. Limits define the boundary of the drawing area in AutoCAD, representing the virtual paper size and model space. Set using the limits command, users specify the lower left and upper right corners. Limits help control the zoom and grid area, ensuring the drawing fits within a defined region. Properly setting limits is crucial for organizing and scaling drawings, especially when preparing for plotting or printing. Plotting, also known as printing, is the process of sending a CAD drawing to a printer or plotter to produce a physical copy. The plot command opens a dialog where users set the printer, paper size, scale, and plot area. Plotting ensures that digital designs are accurately translated into tangible documents, essential for construction, manufacturing, and client presentations. Snap mode in CAD forces the cursor to jump to exact, predetermined increments in the drawing area. When snap is on, the cursor moves in fixed steps, making it easy to draw precisely. Snap is toggled with the F9 key or the snap command. Setting snap spacing ensures consistency and accuracy, especially when creating geometric shapes or aligning elements. AutoCAD supports several systems for entering points. Absolute coordinates specify points relative to the origin. Using the format X, Y, relative coordinates use the @ symbol to indicate offsets from the last point. Polar coordinates specify points by distance and angle from the last point using a distance angle. These systems provide flexibility for drawing lines, shapes, and complex geometries with precision. Computer-aided engineering, or CAE, includes software tools for simulating, analyzing, and optimizing engineering designs. CAE covers finite element analysis (FEA), computational fluid dynamics (CFD), and motion simulation. Engineers use CAE to test virtual prototypes, reducing cost and time before physical manufacturing. CAE is integral to modern product development, ensuring designs meet performance requirements. Computer-aided design and drafting, or CADD, extends CAD by incorporating drafting capabilities. CADD software combines geometric design with technical drawing standards, producing engineering drawings complete with dimensions, annotations, and title blocks. AutoCAD is a prime example of CADD, streamlining both design and documentation processes for engineers and architects. Computer-integrated manufacturing, or CIM, integrates the entire production process using computers. CIM links CAD, CAM, and business systems like ERP into a unified system, creating a fully automated smart factory. This integration streamlines design, manufacturing, quality control, and inventory management, enhancing efficiency and reducing errors in production. Computer-aided manufacturing, or CAM, uses software to control machine tools and production equipment. CAM translates CAD designs into machine instructions, such as G-code for CNC machines, enabling automated, precise, and efficient production. CAM bridges the gap between design and manufacturing, ensuring products are made accurately and consistently. Material Requirements Planning, or MRP, is a production planning and inventory control system. MRP determines what materials are required in what quantities and when based on the production schedule and bill of materials. It ensures material availability, minimizes inventory levels, and plans manufacturing activities and delivery schedules, optimizing workflow and reducing costs. Finite Element Method, or FEM, is a numerical analysis technique used in CAE to solve complex engineering problems. FEM divides a complex object into smaller finite elements and applies mathematical equations to analyze stress, strain, heat transfer, and deformation. This method is crucial for optimizing designs and ensuring structural integrity before manufacturing. Product Data Management, or PDM, tracks and controls data related to a product throughout its lifecycle. PDM manages CAD files, drawings, specifications, and change orders, ensuring all team members work with the correct and current version of design data. PDM is essential for collaboration, version control, and maintaining data integrity in complex projects. Material Requirements Planning aims to meet three main objectives: ensuring material availability for production and delivery, minimizing inventory levels by ordering materials only when needed, and planning manufacturing activities and delivery schedules. These objectives help prevent production stoppages, reduce holding costs, and ensure smooth workflow and on-time delivery. Technology drawing uses four main types of projections: orthographic, isometric, perspective, and oblique. Orthographic projection represents 3D objects with multiple 2D views using parallel lines. Isometric projection tilts the object so all axes are equally angled, giving a realistic 3D appearance. Perspective projection mimics human vision with lines converging to vanishing points. Oblique projection draws the front face in true shape, with receding edges at an angle. Each method serves different visualization needs. Draw a rectangle in AutoCAD, type RECTNG or REC in the command line. Specify the first corner point by clicking or entering coordinates. AutoCAD prompts for the other corner, which can be specified by clicking, typing relative coordinates, or using options like dimensions, chamfer, fillet, elevation, and thickness. Press Enter to complete. The rectangle is drawn as a single closed polyline object, ready for further editing or annotation. Display the grid in AutoCAD, press F7 or click the Grid Display button. The grid appears as dots or lines over the drawing area. To set grid spacing, type grid in the command line and enter the desired value. You can also adjust settings in the Drafting Settings dialog, setting X and Y spacing independently and enabling adaptive grid. Proper grid settings improve drawing accuracy and speed. Control Autosave in AutoCAD, go to the Tools menu and select Options or type Options in the command line. In the Options dialog, click the Open and Save tab. Under File Safety Precautions, check or uncheck Automatic Save to enable or disable it. Set the minutes between saves as needed. Autosave files can be recovered after a crash by renaming them to DWG, ensuring your work is protected. CAD design systems offer numerous advantages. Increased productivity allows faster creation and modification of designs. Greater accuracy eliminates human errors. Easy modification means designs can be quickly edited. Design reuse enables the use of previous drawings and templates. Better visualization with 3D models helps clients and designers understand the final product. Simulation and analysis integrate stress and motion study. Standardization enforces consistent drawing standards, and digital documentation makes storage and sharing effortless. Snap mode in AutoCAD can be toggled by pressing F9 or clicking the Snap mode button on the status bar. To set snap spacing, type snap in the command line and enter the desired increment. You can also adjust settings in the Drafting Settings dialog, setting snap X and Y spacing. Snap mode ensures the cursor jumps in specified increments, making precise drawing easier and more consistent. AutoCAD offers different save commands. Save Ctrl+S saves the current drawing using its existing file name and location. Save as allows saving under a new name, location, or format. QSAVE is the quick save command, directly saving without prompting. Understanding these commands helps manage files efficiently, ensuring your work is preserved and organized. AutoCAD uses the measurement system variable to determine units and hatch patterns. Measurement equals 0 uses imperial units, inches, loading templates and patterns based on the imperial system. Measurement equals 1 uses metric units, millimeters, loading metric patterns. The UNITS command specifies the type and precision of units displayed. Choosing the correct measurement system is vital for international projects and standardization. Two common line drawing algorithms in CAD are Bresenham's line drawing algorithm and the digital differential analyzer (DDA) algorithm. These algorithms efficiently determine which pixels to illuminate when drawing straight lines on raster displays. Bresenham's algorithm uses integer arithmetic, making it fast and suitable for hardware implementation, while DDA uses incremental calculations for line generation. Bresenham's line drawing algorithm is an efficient method for drawing straight lines between 2 points on a raster display. It uses integer arithmetic to decide which pixels to illuminate, avoiding floating point operations. The algorithm calculates a decision parameter at each step to determine whether to increment y at each step. This approach is fast and produces smooth lines, making it ideal for real-time graphics and hardware implementation. Asterscan displays sweep the screen row by row, refreshing the entire grid of pixels many times per second. Images are stored in a frame buffer as pixel color values. Random scan displays or vector displays direct the beam only to parts of the screen where lines need to be drawn, tracing lines directly. Raster displays are suited for complex, shaded images, while random scan displays excel at sharp, wireframe graphics. Beam penetration technique is used in CRT displays to produce color images. The screen is coated with layers of colored phosphors, typically red and green. By controlling the speed of the electron beam, different depths of phosphor layers are excited, producing red, green, orange, or yellow. This method offers limited color range and quality compared to modern shadow mask techniques. Emissive displays generate their own light directly from electrical energy. Examples include CRT, plasma LED, and OLED displays. Non-emissive displays like LCD and e-ink modulate external light and require a backlight or ambient light to be visible. Emissive displays are generally brighter with wider viewing angles, while non-emissive displays are more energy efficient and suitable for portable devices. CIE-XYZ color model is a mathematically derived color space based on human visual perception. X, Y, and Z are imaginary primary colors, ensuring all visible colors have non-negative coordinates. Y represents luminance, while X and Z encode chromaticity. The XYZ model is device independent and serves as a reference for converting between color spaces like RGB and CMYK. It's fundamental for color management in digital graphics in CAD.